Okay, in this video we're going to be doing Calc AB Problem Set 98. Problems and playlists in the description below. Let's take a look. Number 1, find the horizontal asymptotes of f of x equals 8 minus 5 to the x over 4 plus 5 to the x. The most important part of this problem is really that this is not a rational function, which means it can have two different horizontal asymptotes, and we have to consider that. So we got to go to infinity and negative infinity. Let's go to infinity first. So I have limit as x approaches infinity of the given thing. This, what you're going to want to look at is the dominant term. So in the numerator, what is the dominant term? It's 5 to the x. In the denominator, the dominant term is 5 to the x. I'm going to divide everything I see by 5 to the x. So I'm going to get the limit as x approaches infinity. I'm going to have 8 over 5 to the x minus 1 over 4 over 5 to the x plus 1. Now if x approaches infinity, 8 over 5 to the x goes to 0. 4 over 5 to the x goes to 0. All that's left is negative 1 over 1, which means this is negative 1. Therefore, we can definitely say that y equals negative 1 is one of the horizontal asymptotes. We also have to go to negative infinity because we could get a different answer. For a rational function, which is a polynomial over a polynomial, you will always get the same answer to infinity and negative infinity if there's a horizontal asymptote, not the case for other functions. So for this one, what I like to do, it's a different technique. I like to just think about the graph of 5 to the x. So 5 to the x, if you go to negative infinity, is definitely going to approach 0. With that information, looking at what we have 8, which is unaffected by x. We have a 5 to the x, we have a 4, which is unaffected, and then we have another 5 to the x. So we really just get 8 minus 0 over 4 plus 0. That's 8 over 4, which is 2, which means that y equals 2 is also a horizontal asymptote. So this is an example of a function with two different horizontal asymptotes. Well worth remembering. That's like a really good classic AP multiple choice type problem. All right, let's take a look at the next one. All right, use the graphs of f and g above to answer the questions. I'll tell you ahead of time, somehow I screwed up when I was making this problem and it didn't work out the way I wanted to. But I mean, the work will be just as valid. It's just neither of these limits will end up existing. So let's take a look. So if we're doing the limit as x approaches negative 2 of g of f of x, the first thing we have to do is consider what happens on the graph of f of x as x approaches negative 2 from the left and the right. So I'm going to just take it from the left. So if x approaches negative 2 from the left of f of x, which is like the inner function, what happens on that? Well, if I approach negative 2 from the left, you can see there I've kind of traced it out in yellow. I'm going to approach 1, but from above. So I'm going to say 1 with a little plus. So now what I need to do is consider what happens on the graph of g of x as I approach 1 from above, because that's kind of the order of operations here. So if we do this, go to the graph of g of x and approach 1 from the right. So 1 from the right gives us 2. And now we have to go back to the original and approach negative 2 from the right. So it would be the limit as x approaches negative 2 from the right of f of x, the inner function. Go to the graph, approach negative 2 from the right, and you get negative 1, but from below. So negative 1 from below. I can actually tell you what I did wrong. When I was reading one of the graphs, I thought that x equals negative 2 was actually x equals negative 1, and that kind of messed up my notion of what was happening. But it doesn't matter. Now we got to look at the limit as x approaches negative 1 from the left of g of x, the outer function. So go to the graph of g of x, approach negative 1 from the left, which I guess I did. I wasn't paying attention. Sorry. Okay, I'm going to approach. Oh, it's because I highlighted it at the same time, right? Look up there on the red. We're going to approach. There you go. You're approaching negative 1 from the left. You can see that you approach negative 2. So at this point, we needed these two values to be the same for the limit to exist, and they're not the same. So this is a DNE situation. We're going to do the next one and unfortunately get kind of the same result, but it's like the logic that really matters. So here we're doing the limit as x approaches negative 1, f of g of x. So first you worry about what g of x is doing from the left, figure out correspondingly what f must do, then you'll go from the right. So step 1, limit as x approaches negative 1 from the left of g of x. So I look at the graph of g of x, I approach negative 1 from the left, like that, and I get negative 2, but from above. Negative 2 from above. I thought I made another mistake. So now I need to see what f is doing as I approach negative 2 from the right. So you look at the graph of f, you approach negative 2 from the right. We've already done that once. We're going to get negative 1. All right, so that's negative 1. Now we repeat the process, approaching x equals -1 from the right. So for these limits, you're always looking at one-sided limits, and it's like you really have to do like twice as many limits as you expect. So what is g of x doing as x approaches -1 from the right? G of x is approaching 3, but from below. So that, again, I don't know what I was doing here. Watch, and you can see me highlight it in purple on the graph of g of x. Here it comes. There it is. We're approaching 3, but we're approaching from below. So now we need to see what happens on f of x as we approach 3, but from the left. All right, 3 from the left. Boom, it's approaching +1. It was so close. Like you can see in both of them, I got 2 and -2, then I got -1 and 1. So we needed these to be the same. They are not the same. So this answer is also DNE. I apologize, I guess, because it's like I'm not happy about it. But I mean, limits sometimes don't exist. It's not like it's impossible. All right, next problem. Given g of x is equal to the integral from, well, this is weird. That should be f of t dt. 0 to x, f of t, 5 to the t? Hold on. G of x is the integral from 0 to x of 5 to the t dt. I'll change it because it's like kind of important enough. You have to use a different variable here. So t dt. So we'll use that. Oh, God, I'm like getting everywhere. All right, whatever. I erased the little... Okay, good enough, I think. Find the average rate of change of g of x on the interval from 2000 to 2001. So I'm just going to dive in and do it. Average rate of change is algebra 1 slope, so it's going to be g of 2001 minus g of 2000 all over 2001 minus 2000, which is convenient because that subtraction is just 1. All right, so now what we really have, we're going to go back to the function g and find g of 2001. Just means make the upper bound 2001. Also, I'm going to use x here, and we're just going to live with it. Minus, replace the upper bound with 2000. We get this. So the problem is, this is like, these numbers are insane, right? But one of the properties of definite integrals is the integral from 0 to 2001 minus the integral from 0 to 2000 is just going to leave us with the integral from 2000 to 2001. So I'm going to simplify it like that. And maybe in some universe it's a multiple choice question and this is the answer. Who knows? We can find the antiderivative of 5 to the x. So you have to remember the derivative of 5 to the x is 5 to the x natural log of 5. So the antiderivative will be 5 to the x times 1 over the natural log of 5. So we get 1 over natural log of 5. Also, if you don't like that, you can do a u substitution where u is equal to 5 to the x and just like go to town on the u substitution. That'll definitely work. I just think it's easier to remember it. Fundamental theorem. So first you plug in 2001, then you plug in 2000, and you subtract the results, and then that'll be over the natural log of 5. I think you could probably end it here, but I chose to continue. So you can factor 5 to the 2000 out of both of those things, and you will be left with, in the first case, just 5, and in the second case, just 1. And I thought it looked neater if I wrote it this way. So I wrote my final answer as 4 times 5 to the 2000, all over the natural log of 5. I don't think this was my best problem set, but it was a problem set, and it's done. And I hope this was helpful, and good luck.